Hi, welcome back to pycse. Today I want to show you an implementation of cans in pycse. These were really popular in the last year as an alternative machine learning architecture to neural nets, and we'll kind of talk through what they are and what we can do with them in the pycse implementation. So the big difference is that in a neural network you have fixed activation functions that operate on the nodes. So data goes into the node, it gets linearly exchanged and then non-linearly activated. And cans, in contrast, you can think of them as a learnable activation function on edges. That is, the input will connect to a node, but it gets transformed by a learnable spline function on the edge. And so these are really good for certain classes of models, especially ones that are that have additive functions. That works out really well. So the original paper came out in 2024 on arXiv, and there's another paper here by Arthur Schweitman that talks about global optimization on trained Kolmogorov-Arnold networks. I'll show you a subset of that work where we can convert the can into a MIP and then apply some optimization to get global optimization on the surrogate model. Okay, so it's pretty straightforward to use this. We simply look at the sklearn.can from pycse and import the can module. This is an sklearn compatible interface, and so we can generate some data here, and we make a model like this, and then we call model.fit on our train data and generate a report. This uses JAX. I use a M4 Pro. JAX isn't fully compatible with the Silicon GPU, and so you see some of these pink messages, and that's also why I have the CPU environment variable set up here. Anyway, we also then can call model.predict and see exactly what we want, and this is a fairly simple data set, just part of a sign, and you can see we get a good fit, and it's actually a pretty small network here, only I think 2 nodes, and you'll see why that works in a minute. Now we can see what the learned activation functions are. So I have a plot activations function. Here we pick one layer index, and you can see the 2 activation functions that get learned on the spline, with the spline and how they combine. We can also visualize this network. Here we have the input. These are the edges that connect to the hidden layer nodes, and these are the unique activation functions that get learned on each one. So we have X goes through this and comes to this node, and then goes through each of these and combines to give us the output. And you can see we have a function here that looks remarkably like the data set, and that's why we're able to get such a good fit overall. You can see here how to read this, and we can make larger networks and things like that. Now, something I haven't seen before but was very straightforward to do is add a depose-like character to the can. Depose was deep propagation of shallow ensembles, and the idea here is instead of having a single output, we could have an ensemble of outputs, and then we use a negative log likelihood loss function to give that ensemble the right properties that we desire. And so we can simply add an ensemble here and change the loss type to CRPS. And once we do that, we can get uncertainty estimation on the can. And I think that's a new feature I haven't seen. Depose was reported for neural nets a while ago by Seriati. We wrote an additional paper using depose on graph neural nets, and now here is a concept of putting depose on the can, which allows us to do UQ and see what we get by sampling. It's pretty nice. Even heteroscedastic noise here. You can see it's small noise here and large noise here, and this is a fairly well calibrated uncertainty. There are some hyperparameters you have to choose. This grid size is what determines the spline number of points in the spline. The more points you have, the better it will be, but then the more expensive your model will turn out to be. And you can see here what happens as we change the number of grid points in each spline. We get a better and better fit for larger and larger grid size. The CAN supports multi-dimensional inputs and outputs. So here we have a 3D function, and with the UQ we can do propagation for derived quantities. So here we have an ensemble where we take the exponential of the predictions, and that gives us then some propagation of the error through nonlinear transforms, which is pretty interesting. We also support some regularization. You can put penalty on the spline coefficients. You can put a penalty on the activation outputs. You can do something called entropy regularization. And all of these provide various ways to regularize. You can see what some of the different outputs here are as well. And the last thing I want to talk about is mixed integer program optimization. So one of the things we love about ReLU networks is they can be represented as a mixed integer program, and once you do that, there are tools for finding the global optimum, global minimum of that surrogate model. And it turns out that CANs can be represented as MIPS as well if you limit them in a particular way. So like not all neural networks are MIP representable if you use tanh or some other continuous function. It's only ReLU that becomes piecewise linear. We can specify that we want linear splines and linear activations in the CAN, and that makes it, it turns out to be MIP representable. And then you can use something like Pyomo and a MIP solver, like Gurobi or Cplex, and you can solve them. So this was actually quite a slog to get working fully. It took about a day to figure it out and work it all out. But let me walk you through what happens here. So we're going to create a CAN and then two different neural networks on a additive function here that just has some decomposable periodicity. And we can get by, it turns out, with a quite small CAN to represent it. So here we use a CAN, a 2 by 2 by 1, so 2 inputs, 2 neurons, 1 output, and we only need a grid size of 5 to get a very good test R-squared value. And to get an equivalent value or equivalent accuracy with a neural net, we need to use a much larger one. So here, if we try 10 neurons, we only get to about 0.82. And if we use 2 by 50 by 50, so it's a deeper network with more neurons, then we get more accurate, still not quite as accurate as the CAN, but pretty reasonable. And it is notable that these train very fast. There's some discussion about, the train times and why they can. This is really from using BFGS versus using Atom. They're not the same optimization methods. Where this really changes is when we convert these three things into MIPS. What we get to is we have 30 binary variables for the CAN. For the small ReLU, we only have 10, but for the larger ReLU, we have 100. And so the number of binary variables is sort of what makes it a challenging problem to solve. And so the smaller this is, the better off you are. And if we work out what the solutions are, then we find that, I'll get to the solutions in a minute, I suppose. Here we have the sort of comparison of the number of binaries again. And the key insight here is the can gets better accuracy and a smaller MIP, which turns out to be an advantage when we come to solve this. So we do have to do a little bit of work to install these solvers so that we can use them, and then otherwise this is getting run inside of Pyomo. And we use Gurobi. It's the fastest commercial solver. We get a free academic license, which makes it all work. And we get to a solution with the can. First, we have to export it from the regular form into the MIP form. And then we come down and solve it. The true answer is here. We get a quite close answer with the can, and it doesn't take very long to do that. Compare this to the ReLU network. We can scroll down. Looks like this is sort of repeated a little bit. We have to export our ReLU to a MIP. I do that in Pyomo, and if we find the solutions, where are these? The first solution with the small is not very good. It has 10 binaries, and it is quite fast, but the solution is not good at all. If we use the large ReLU, then we can scroll down a little bit more. This takes a while to export, and then we compare the solutions. It is not much better, and it takes quite a lot longer to find that. And this is a feature that we have not found a good solution, and that's probably because it's not quite as accurate. The R-squared value is lower, and the can is actually quite a lot better in this case. Now, this may not be the most definitive. Of course, one should spend more time trying to get a better ReLU, but you can see it's taking a lot longer, and it's already nowhere close in accuracy. And that's just because it has so many more binaries associated with all the neurons, and we get a much smaller MIP with the can. Okay, so that's just a summary of this new kind of feature in pycse. You can find the notebook up here at this URL. I'll put it in the video description, and you can try out using the can for a variety of other problems that may include global optimization or uncertainty quantification. Either of those alone would make it interesting to try, and may give you better results than other machine learning models for some problems, especially models that are made of additive terms. All right, thanks for stopping by and listening, and see you probably next year.